You may recognize this music, or having heard it before, called Scotland the Brave. I just put it on in honor of James Clerk Maxwell, who was Scottish by origin. So we'll give him a little hello. We could have done the Scottish Symphony, but that's by a German. So this is the authentic Scottish music. And the Scots actually, over time, have contributed quite a bit to science. So we appreciate that. But this man, Maxwell, although he lived only about less than 50 years, contributed enormously to science in the middle of the 1800s. And an unequivocal genius. You will, if you keep studying chemistry, physics, you'll come across Maxwell equations in thermodynamics, having to do with transformation of entropy into various things. You'll come across Maxwell-Boltzmann statistics, and his perhaps most famous work is these Maxwell's equations. And the interesting thing is that of the Maxwell equations, of which there are 4, he contributed about 1/2. But it was a crucial 1/2, as you'll see. Because you've come across already in our work 3 of the equations which are included in Maxwell's equations. 3 of them are already done by other people, as you'll see. So we've moved quite briskly through electricity and magnetism. We're down to just a few more topics. This electromagnetic waves that are a consequence of Maxwell's unification of all the known laws of electricity and magnetism, and the addition that he created, that he put in. So I have again here an outline of the topic. What Maxwell did was come up with a new term, a new current that belongs in electromagnetism that had not been known before. He said that there should be more in those equations, in the understanding of electricity and magnetism. So you have, let me get an arrow here. You have 4 equations that he synthesized, that he brought together, talking about electricity and magnetism. Then you have 2 other equations which you've already come across. That is the Coulomb equation, which tells you the force between 2 charges, and the Lorentz law, which tells you the force on magnetic effects. That is, you have a current and a charge moving. So I have to put my Now the tremendous consequence of what Maxwell did was that he predicted that there could be waves of electric and magnetic influence that could propagate through empty space. And that is an enormous effect which has revolutionized our world. I mean, we use electromagnetic radiation all the time now, hardly noticing it, how important it is. But your cell phones, your TV reception through the air, the fact that you could broadcast back from the moon, pictures of the people walking on the moon, all of that is a consequence of Maxwell's equations. So what I'll do is I'll try to describe waves in general, which you should know about the general properties of waves, and then about electromagnetic waves, how we generate them in general, and the fact that these waves carry energy, which is really no surprise, actually, when you think about it. since we're getting sunlight from the sun by electromagnetic waves, which keep us alive. This is the reason we have life on Earth, is that the sun warms us. And the fact also that the waves carry momentum, that is, they can actually push on things. Okay, so what is the story behind this? See, Maxwell, one way of explaining this is that we have the Ampere law, which you've seen before, of course, and what it said was that if you had a current, if you made a loop around that current, enclosing the current, going in some direction, you could integrate around that loop, and it will tell you the current J, let me make an honest big J, enclosed in that loop over times mu zero. Okay? Now, that's your powerful Ampere law, which is very useful in getting a quick answer for some problems, of the symmetrical problems which we handled. Okay. Now, so the question is, think about it a little bit more. What do you mean by the current that's enclosed? Well, if this is the current that's going, it's as though there's some kind of think of it like a soap film in this loop. And all you're saying is that if the current passes through that soap film, we count it as passing through the loop. That's one way of looking at what we're talking about. Now, in this picture, now the current comes along, and then suppose we have here a capacitor plate, our famous capacitor plates like this. Okay? Now, here it's pretty clear that if I make an integral around this loop, I capture this current passing through the soap bubble here. But suppose I make the soap bubble, like kids will, like this. Now this current, this actual current, reaches here, and as we've said, many times, all it's simply doing, if there's a current coming here, it's delivering, say, plus charge to this plate. And we've said that no real current passes between the plates. So on first glance, you would say that J is equal to 0 between the plates, or I, current density, or what? Oh, I had J here. Well, let it be I, the current. Current density or current would be similar. Okay, so let's call it current. So there's no current passing through that extension of the interior of the loop. So something's funny here. On the one hand, this says I have magnetic field over here because it's current passing through it. But if I look at that bubble, there is no current passing through that bubble. So now it's saying that there should be no magnetic field over here because there's no current over here. So that's one way of saying there's something missing here. And we can derive a way of solving this by considering that, in a way, charge is accumulating on this plate. As we went over this, in the review session last time in quite some detail. But all you have to say is, let's try to make a current out of what's actually happening on that capacitor plate. So charge is arriving there. When this current is changing, charge is building up. So you have a kind of current. You have a kind of dq dt, which is from the law of the capacitor. It's a dv dt, or the voltage is building up on this capacitor, and charge is arriving here. So if you like, we could define dq dt as a displacement. We call it the displacement current. And when you look at it, let's see, you have V over D is the electric field. V is given by Q over epsilon A. Right, because that's the definition in a parallel plate capacitor. So here, just by multiplying across, you get that Q is epsilon EA, and EA is the electric flux, a field times the area. So dq dt is then given just mathematically by the rate of change of the electric flux with time. So if you take that, in other words, say that there is a current in here simply because the electric field is changing in time, and you have a changing electric flux between the plates, let's call that a current, because that's the current that is sort of arriving at the plates. Let's just say that it continues through the plates. Now, that seems a little far-fetched, perhaps. Now, I think where Maxwell got this idea, and why does he call it displacement current? See, nowadays, we think that there is just empty space through here, an infinite resistance here, so just empty space. In Maxwell's time, they thought that space had something in it. So you could imagine if I'm building up an electric field here, if there was something in that space should polarize. If space had something in it, then the molecules should polarize of the space. And so if the electric field is varying, you have kind of a current. You have a little current going this way and a little current going that way, or a charge going that way, which is yet another current. That's a negative current. So the alternating electric field, if the medium was polarizable, it would have a kind of current in it. It's a displacement current. It's just a displacement of the imagined stuff of space. That was, I think, what was in his mind. And so that would produce a kind of current which would allow for the continuity of the electric current through the capacitor. It's not real charge, it's just the polarization charge, the displacement of these imagined material of space. Now, nowadays, we don't think space is material and is polarizable. We think of it as really empty, to speak that way. But the idea is satisfying in that it allows for this continuity of current through the capacitor. In any case, what it means is that we have to add to the Ampere law the Maxwell contribution. And say that if you go around a loop, you have to count not only the real current enclosed, but also epsilon naught, the electric flux, times this. So this term here is is to be treated like a current that can produce a magnetic field. A change, so the original Ampere law applied to steady currents. You have a steady current, it'll produce a steady magnetic field. If the flux is changing, the electric flux is changing someplace, it produces yet another current, which should be counted in creating magnetic field. So, is that a big deal or not? Yeah, it happens to be. So the final Ampere-Maxwell equation, Ampere being the first term, and this being the Maxwell displacement current, which is due to the fact that the electric field is, if you will, polarizing space, which, you know, that idea is no longer in fashion. But the point is, it works. It works. And it's been measured. Actually, what you can do is make a capacitor like this, put a loop inside here, and see if you get any magnetic field. There's no real current passing through. But if you put a loop here, you'll actually pick up magnetic flux due to the fact that the electric field is changing. Okay? So, in a way, you can say there's a little justification here, or you can say it's a whole new law. Like the fact that, as Faraday said, that you can get an electromotive force by taking the change in the magnetic field with respect to time. Where does that come from? Well, that's just the way nature works. It's not terribly obvious, perhaps, but that's the way nature works. And you could say the same thing here, that nature works in such a way that if you have a changing electric field with time, it acts like a current and will produce a magnetic field. So you could say this is just an observational fact. And so we end up with, as I said, 4 equations which are all called together collectively the Maxwell equations, although the first one is basically Gauss's law, which is Coulomb's law, you know, in another form. Namely, you have an electric field integrated over a surface, and that will give you the charge enclosed in that surface, within the surface, which you've seen before many times. Then you have the analog of Gauss's law for magnetism, which says that the magnetic field integrated over a surface will give you 0, and that says there is no magnetic charge yet ever discovered. So that's another of the Maxwell laws. And then you have the Faraday law, that the electromotive force, or the induced EMF, which is this electric field integrated around a loop, that's another way of writing that law, is the rate of change of the magnetic flux with time, with a minus sign due to lengths. These 3 you've seen before. And here's the 4th one. This is the Ampere. This is the Ampere part here, steady current. And this is Maxwell's part. As I say, 1/2 of the 4 laws is Maxwell's contribution. But it's very important, it turns out. So these are the famous Maxwell equations. And well, the amazing thing was that Maxwell, once he got this idea of the displacement current, he put it into his mathematics, and he saw that there could be waves of electric and magnetic fields that were appearing in that equation, those equations, 4 of them, that there could be waves that come out of that. So, again, let me review them again. What the equations do is they tell you how the electric fields are generated, which you knew before, namely electric charges by Gauss's or Coulomb's law, create the electric field. To make magnetic, the other way to create an electric field is by that Faraday law. Because this electromotive force is also written as the electric field around a loop. The distance is the change of the magnetic flux with time. So a changing magnetic field creates an electric field around the loop and can drive current around the loop, so it's creating an electric field, or you could think of it as an electromotive force, equivalent things. So there are two ways of making an electric field. Magnetic fields, on the other hand, according to what we know, there are no magnetic charges. There are dipoles always, north and south. So you get a Gauss law, but it says that the integral of the B field around a surface will be 0. But to create a magnetic field, you either have a moving electric charge, moving in a steady rate, you get Ampere's law, steady current will produce a magnetic field around it, or this Maxwell induction, you could have a changing electric field through a loop, and it will produce a magnetic influence around it. So the changing electric field creates a current, which creates a magnetic field. And then we have the force laws, which say that the force from an electric field is just the charge times the electric field, or the magnetic force is created by a B field in which there is a moving charge, Q, moving at a speed v, and then you have this cross product, or you can write it as the B field crossing with the current and the length of the current element will give you the magnetic force. Again, this cross product. Okay, so where do you get waves out of this? That was the big thing that came out of this, because up till now, he had adapted the laws that he already knew. So how do you get waves? Well, I'll say it very briefly. Now, to have a wave in free space, we're assuming now, going back to going back to these equations. Let me see. So go ahead. See, we can use Gauss's law, but previously we had a charge over here that was charge enclosed. But in free space, there's no charge. And we have the Gauss law for B. Then we have the Faraday law. Well, that doesn't involve real charge. But then we have the Ampere-Maxwell. It had a current term here, the steady current, which would be like a wire. But in free space, there are no wires. There are no free currents. It's just empty space. So all you're left with is this rate of change. Only the rate of change of the electric field in free space is acting like a current. So these are the equations of Maxwell when applied to free space. And so if you look at these, I'm not going to derive a wave equation out of this. I'm just going to sort of roughly indicate it. The point is that the changing magnetic field produces an electric field. But the changing electric field produces a magnetic field. So these two things bootstrap each other. If you have a changing electric field, it'll produce a magnetic field. The changing magnetic field creates an electric field. The changing electric field produces a magnetic field, which produces an electric field. And you go on and on. They bootstrap each other. They just keep working on. And so that's why it can travel through empty space without having any charge or current in that space. So that's as far as I really care to give a derivation. By the way, it's in the book, a derivation, and at the end of my PowerPoints, I try to fill in some of the little details that may be confusing if you really want to go through the derivation. It's within the scope of what we know. Let me just put it that way. But now I want to go on to, this is perhaps an important slide, because I want you to know the properties of waves in general, because you're going to come across waves in a lot of your studies. For example, some of you who go into medicine will do ultrasound. It's a wave. You're going to do CAT scans. That's a wave. It's an X-ray. You're going to do you may do diathermy or induction. We were talking about transcranial magnetic stimulation, which involves transient electromagnetic fields. So here I've listed this, and we'll also use the same thing when it comes to quantum mechanics, because later on we can do quantum mechanics. It turns out, as you know, that one of the important ideas in quantum mechanics is that material particles have wave-like character. So the point I'm going to make then is that if you knew all these properties of waves, and you were a scientist in 1925 when the idea came out that material particles were waves, you could just run down this list and check to see, let me check the polarization of matter. Let me check the energy, momentum, pressure, reflection of matter, total internal reflection, refraction, diffraction, interference of matter. If you verified any of these, you'd probably win a Nobel Prize, because you were showing that matter is wave-like, and all waves should have all of these, well, at least most of these properties. And so if you know the general properties, you just go ahead and look for them, and you've made a discovery. And people did. I mean, you could get, reflection of electrons, refraction of electrons is measured, diffraction of electrons won a Nobel Prize, interference and diffraction won Nobel Prize. Standing waves, you could see them. There's famous pictures of standing waves of electrons done with scanning tunneling microscopes, and it's in all the textbooks now. All I'm saying is that you should know the general properties of waves, and we'll see how the electromagnetic waves participate in these properties. Okay, well, the other thing I want to say very, very briefly about the form of a wave. A wave varies, just think of a sine wave. It varies in space, and it also varies in time because it's moving. It's a moving wave usually. So that's why a typical wave equation, pardon these symbols, this curly D, it replaces your normal derivative sign, but you see the wave having both, you see it has a space part and a time part because a wave moves in space and time. So when you take a derivative of something like this, you have to say derivative with respect to what? Derivative with respect to x or derivative with respect to t. So we have this symbol partial derivative with respect to x. So if you see something like this and you mean to say take the derivative with respect to x, you put a partial derivative. It's no big deal. It's just notation because you have something which has more than one variable in it. So you have to say here what I'm doing. So I'm having here the derivative, take two derivatives, but with respect to space. And here I'm taking two derivatives, partial derivatives, with respect to time of this function a. So it's just an extension of ordinary derivatives. The important thing is that a traveling wave has a space part and a time part. If you keep the time constant, you'll see variations in space, and if you keep the space part, you'll see it bobbing up and down in time. But the important thing also is that there's an amplitude, and the amplitude it could be anything. It depends on what the stuff is that's waving. It's not the same as a distance. It may look like a distance, but it isn't. It could be. But in the case of electric waves, it's the amplitude of the electric field that's going up and down. So that could be an electric field. Or if it's a water wave, Well, a water wave you might want to measure by its height, or you may want to measure how many gallons are in that water. So it could be gallons per second going by. So that amplitude, you have to see what it is. In the case of sound waves by which you're hearing me, it's a pressure thing. So that A there, the amplitude would be the amplitude of the pressure that is varying in time and space. So because a lot of people make the mistake, they see this amplitude and they think it's a length. It's not necessarily, it could be. For example, a vibrating string, you could say the amplitude is the height of the distance. It's deviating from the string. It could be a height, or it could be, that would be a reasonable place to use the amplitude as a height, but it doesn't have to be. I just warn you in advance because I've heard that from other students. They think it's necessarily a length. No, it's the stuff that's varying. And here is an example of where, for example, I have a wave which is, say, frozen in time, and if I go along its length, I'll see it varying up and down in space, and the wavelength, you well know probably, is the distance between like points on the wave. It doesn't have to be the crest necessarily. It could be between, say, here and here, or here and here, but it's the length between like points. That's called the wave length, and that is a distance. That's meters or centimeters or what have you. It's a length. On the other hand, you could have a thing that's frozen in space. In other words, you stay at one place and you see what happens in time, and you'll see the wave in time bobbing up and down, and the time between like points is called the period of the wave. It's the time between cycles. Staying in one place, the time it takes for the wave to bob up and down. And that's the inverse of the frequency, which is how many cycles per second. And that's related to this angular frequency. How many angles is swept out in a second. So these are definitions. You really have to, know them. And the velocity of the wave is given by the distance it travels by the time it takes, which is the time is the inverse is the frequency and the wavelength. So the velocity of a wave is the frequency times the wavelength, or it's by definitions the angular frequency divided by the wave vector. The wave vector is the number of 2 pi's per wavelength. So these are all things, just simple math. Now, in the particular case of the electromagnetic wave, we have this model here which shows you somewhat graphically how an electromagnetic wave is. You see, because the two things are feeding on each other, the E and the B, I don't know if you can see that there is a magnetic thing, the red, like that, and the two fields grow together and reverse. See, you go up, here's the way it goes, and the B field, and the two are at right angles to each other. That's a feature of electromagnetic waves. We call that transverse, because the direction in which it travels is another interesting point about electromagnetic waves. These are all things that you're expected to know. Namely, if you have an electric field in one direction, the magnetic field is perpendicular to it in free space, and the direction in which it propagates is the direction of E cross B. That's one way I remember. In other words, turn E into B, and the direction of motion is in this direction. The speed is going in that direction, it turns out. A lot of this you'll have to take on faith, unfortunately, because it all comes out of the equations of the wave motion. But so I'm afraid I don't like to do this, but you just have to take it on faith. And Okay, so that's the general shape of things. And the wave has this, doesn't necessarily have to be sinusoidal, mind you. You can have pulses, which are made up of sinusoids and so on. But so you'll have an amplitude, which is an electric field, and you could have but they will be perpendicular and travel in the direction of E cross B. So again, what happened there? Microsoft error. Oh my goodness. Maybe it'll recover. Here we go. Excuse me while I get this back. Back to the beginning. All right, we'll swiftly go through a review of this. The displacement current is caused by the changing electric field, and the nice thing is that even happens in empty space, and that makes all the difference here. So we have these equations. We have waves. We have a wave which varies in space and time. We have wavelength and period of the wave. There's a model. Here is the, again, those two equations acting in empty space. They generate each other. And unfortunately, here's the full-blown wave equation, which I shall not bother you with. The interesting thing was, in this wave equation, you come out with some place where it says what the speed of this wave is. When you get all down to it, it comes out to be this number here, when Maxwell got through with his equations. And it turns out that the speed of this wave turned out to be, because you see the equations really started out from electrostatics and electrodynamics, mu and epsilon. Those mu and epsilon are carried along in his derivation of the waves. And it ended up, when he saw the velocity of this wave, it became, as luck would have it, the square root of epsilon naught mu naught. Now, I won't go through it, but you can just look up on the cover of your book what are epsilon naught and mu naught and plug them into this little formula, and it will turn out that the velocity of this wave is 3 times 10 to the 8th meters per second. Now, they had measured the velocity of light by reflecting things, a very hard thing to do, but clever experimentalists had measured the speed of light, and it was just that value. So Maxwell said these waves of varying electric and magnetic fields that I predict in free space light must be of a character, because I'm getting that all electromagnetic waves travel at this speed. And so he said that light, which nobody knew exactly what it was, he said it's an electric and magnetic phenomenon. Who would have thought? Who would have thought, starting with Coulomb's law, that you're going to end up with light waves, that light is coming out of Coulomb? Who would have thought that from ampere you have a wire and you have a mu times the current, that's going to end up explaining light? That's what's so fantastic about what Maxwell did. It just came out of the blue and the red and the green and all those nice colors. Who would have thought? And and he also predicted that there's another feature here, that the ratio of the E and the B field would be given by the speed of light, and that all of them would travel, all of these waves would travel at the speed of light in a vacuum, the same speed, which is interesting too. And he says that, any frequency or wavelength is possible, just so long as they will maintain this ratio and they will travel at the speed of light. So in a way, he said, not only is light of this character, you could look for other things of this character. And of course, I have this famous, you can get this T-shirt where God said, Maxwell's equations, and then there was light. Now, that's very a little bit, shall I say, blasphemous, but Max one he was right. It doesn't contradict anything. It just depends how you derive things. So in all cases, we have that the velocity of light in vacuum is the speed c. If you try to pass light through a different medium, a denser medium, it will slow down, and the velocity in a medium will be different from c. We'll get into that. That's how we make lenses and stuff like that. The glasses that I'm wearing work because the velocity of light inside my glasses is not c, but it's less because of the slowing down due to the glass. And also in real media, the velocity will also depend on the frequency, turns out, and that's a very interesting phenomenon. But n is so-called refractive index. It's the slowing down of the light in a medium. But in a vacuum, you'll get always all the electromagnetic radiations travel at this speed. Let's see what else we have. Okay, and then you have this ratio of the magnitude of the E and B fields that are traveling together will be that speed. And they're perpendicular to each other and perpendicular to the direction. And the direction of propagation is that. Now, I just wanted to throw in this, just kind of historical thing. In April of 1913, just about, 102 years ago, almost to the day. Well, it's now March, but this was April 12th. The Titanic went on its maiden voyage from Southampton to New York and was steaming full steam. You know the story. You've probably seen the movie. I should play the music. Do you know the music to the Titanic? But I just point this out because do you see these masts? This is not a sailing ship. There's a four-masted, four-funnel steamship going at record speed. It was trying to set a transatlantic record, on its maiden voyage. These masts here were actually radio antennas because radio had been more or less developed by Marconi. He had been able to broadcast from England to Newfoundland in Canada in 1901 or 2 or 3, something around there, and he actually won a Nobel Prize for that. So they could telegraph. So they were starting to outfit luxury liners with radio in those years. So this is 10 years after Marconi's thing. And so the Titanic, there is, if you see it clear, there's actually, if you can see it better, there's an antenna strung between these two masts. So the ship had they had telegraph. It wasn't voice, it was telegraph. So you go da da. So the rich men on the ship could telegraph home to New York. Oh, I'm having a great time in the salon, and and we're having a ball, and how are my stocks doing, and all these important questions could be telegraphed to New York, and they would get answers, and everybody was having a ball on the ship. Until on the night of the 14th, they hit the iceberg about midnight on that night. But the thing I bring up is that they did have telegraph on board. And so the telegraph operators started calling for help. And fortunately, there was a ship about 60 miles away, which also was outfitted with a telegraph and picked up the signal and came to their rescue. It would never have known. Here's a ship in the middle of the night, 12 midnight, sinking. It sank. It took about 4 hours to sink. So by 3 in the morning, it was at the bottom, in the pitch dark, in the middle of the Atlantic, among the icebergs. But the Carpathia picked up the signals, and I read about this yesterday. It was just amazing. He turned off all the hot water to the ship so that every bit of steam possible could be used to drive his ship to rescue the Titanic. And he arrived, I think, a couple of hours later, because I guess they go about 15 knots, 15 miles an hour. He arrived, the ship, I think, was already sunk. But they rescued 700 people out of the lifeboats, at least. But can you imagine if they didn't have the telegraph? Nobody would have known. The guys would have been floating around in the middle of the freezing water, and nobody would have just known. So it gives me a feeling that how courageous these sailors used to be. Imagine going out into the ocean with no communication. You're in the middle of the ocean and you can't do anything. You can't call anybody if anything bad happens. What guts it must have taken to sail the open sea. That's amazing. But fortunately, since then, we have a radio and telegraph to do that. Wireless, very important. Up till then, I think they had already laid a cable to carry things underwater, but that wouldn't have helped these folks because they couldn't pick up the phone and dial up New York and say help. But by 1905 and 6 and 7, they were outfitting these things. Anyhow, I think it's cute. Actually, it was 3 years ago I gave the course, and I could say, 100 years ago, the Titanic sank in April, and that's how we saved them. So the point is, let me point out that, again, you can make electromagnetic radiation of all kinds of wavelengths and frequencies nowadays in all these years. I give you a thing. All these frequencies are very valuable because what you can send information on each channel, each frequency, and hopefully isolate them. So we have the Federal Communications Commission assigning certain frequencies to certain uses, and the whole spectrum is used up, and it's very valuable territory, and that's worth millions. I have another story of some Indian fellow who was in charge of India's spectrum, and he was selling it off to his friends for bribes because the spectrum is so valuable. And they caught him, and I think he's in jail right now, unfortunately. But this spectrum is very valuable, so people fight over it, like who's going to own the broadcast bands. And you have to go to the FCC and explain to them why we should give you this public space to use your radio. So KGO or KCBS has to explain the public benefit of why they are assigned this space. So let me show you a typical radio generator here. This is a little generator of a radiation of about 85 million cycles per second. And it's radiating here. And this is an antenna, and it's picking up this thing. If I go away, you see it's not very strong. But if I get closer, I want to show you that, it's starting to pick up. It gets brighter and brighter as I get closer. It goes down sort of as 1 over r squared. Now, the interesting thing is that what this thing is doing, it's sending electrons up and down these wires, and they are creating an electric field which is sending electrons up and down these wires and lighting up the bulb. One of the things I want you to see is that since the electric field is this way, if I put the thing this way, the electric field is trying to make the current go that way, but it's not going to go through the wires that way, right? It's not going to really drive current. So you get nothing here. Whereas when it's parallel, because the electric field can, this is something, again, first principles, you could figure this out. The other thing, it doesn't radiate in this direction. Because the electric field is going back and forth this way, it's not really shooting out anything from the end. So you have a radiation pattern coming forward in something like this. So this is a fairly typical radio transmitter. You can go down to the bay and you'll see tall towers sitting in the bay. Basically what they are is sending out radio waves. We got a few more minutes. The other thing I wanted to remind you, that the way this thing works is that they have accelerating charges. You have to have acceleration. The point being that if you can't get a wave if the charges are just moving uniformly, because then just think, I could get into the frame of reference of that charge and it would just have a static charge. So you have to have acceleration. in order for there to be a wave. That's a very important point in how these things. So what that thing is doing is driving electrons up and down that tower. When you go home tonight, I want, as I pointed out, you have tall towers, some of them standing in the bay, and notice this, you know this tall structure on San Francisco on the hill, the Sutro Towers? What that is a collection of antennas. Most of your TV and radio stations, especially the FM, have antennas all up and down this tower. So what that is doing, because it's high, it can broadcast to the whole Bay Area from the Sutro Tower. So that's what's going on there. The other thing I want to point out to you is polarization effect. Now this is an interesting point. You saw that, and it's not very obvious, but I want to make it for you. And that is that when the antenna works, you know, if you have your transmitter, you have your transmitter and you have your receiver over here. Now, when they're parallel, the energy goes out and it drives this, so some energy is delivered to this wire. And on the other hand, when the wire is perpendicular to this, no energy is delivered here. It goes to zero. And here's energy is delivered. So, if you want to absorb energy, you would put the wires this way. So here's the thing. This is another source of electromagnetic radiation. The radiation here, let me turn this one toward you. This one is no radiation. This is a receiver. You see there is a thing, it's a waveguide, which is about this big. I don't know if you can see it. It's about that big. What is happening, this is going to radiate. It's going to be picked up by this horn. And so this is electromagnetic radiation. The sound you hear is we convert that to sound so you can hear it, because you can't see this radiation. This is the microwaves. This is sort of like what's in your cell phones or your microwave oven. Now, the question is, if I put a grill like this between here, which will block the radiation more? This way or that way? It's a little bit not obvious. Oh, I should make one caveat here. Looking at the radiating side, namely this waveguide, the electric field is this way, it turns out. It has a pattern that looks something like this, but it's vertical.